Good morning. Thank you very much for inviting me to this amazing conference. And although we are here in a warm Mediterranean climate, I will talk about icebergs. But don't worry, Postgres is able to cooperate with icebergs very nicely. So let's dive into this topic. I work for a German company, Credative. We offer support for open source products, and Postgres is one of our biggest topics. Here are a few words about me. I had quite colorful professional life. I worked with many different databases, with different data processing technologies. In last 3 years, I dived also deeply into large language models, AI, and machine learning. And if you are interested in slides and recorded talks, here you can use these QR codes to find them. Uh, at the very beginning, I want to acknowledge that my talk is actually inspired by words of Simon Riggs. Here is a quote he said in his talk on Prague Postgres conference in December 2023. He mentioned that over the course of next 20 years, everything will be done in Postgres, very much the same way as Linux replaced almost every other operating systems. And I believe that this vision is going to be true. So let's dive into this specific topic of Data Lakehouse, which actually illustrates his words very nicely. So, Data Lakehouse, this is the right way. We all lived through the era of data warehouses and data lakes, and we witness their glory and their downfall because of their limitations. Data warehouses, classical data warehouses are centralized repositories for stable, structured data, and they suffered all those problems of classical proprietary databases. They have rigid schemas, which limit flexibility and adaptability. Scaling is costly, usually possible only vertically. And they use engine-specific data formats, so it's closed architecture. As a reaction on these limitations, people developed data lakes, and they allow to store all data types at massive scale, but without governance, they quickly turned into unmanageable data swamps because people were throwing new and new data into this repository, into this storage, and they sometimes hoped that some magical software will actually do data discovery for them, and they did not care much about structure and data consistency and data integrity and all this stuff which seemed to be boring and limiting. But it turned out that without these proper rules, we just have a huge amount of data and we don't understand what we actually have. So out of these problems, data lakehouses have been born. They merge the best of both worlds, warehouses and data lakes. And data lakehouses allow to store all types of data, structured, semi-structured, unstructured. And they use low-cost data stores like cloud object storage. And what is important, they separate storage from computation. Each can scale independently, but they also implement things which were good in data warehouses. They ensure strong data consistency and integrity, meaning mainly ACID transactions. They add structures and management features and provide catalog layer for access control and data lineage. So they brought the order into this chaotic swamp of data lake houses. If we look at the data lakehouse architecture, we can talk about two main parts, lower decks and upper decks. Lower decks is all that part about data storage formats, processing pipelines, and the different layers of data. Here is classical structure, ideal structure of data lakehouse, and we usually talk about these layers: bronze layer, which ingests raw data; silver layer, where we filter, validate, and clean data and put them into a structured format; and the gold layer, where we model dimensions, calculate aggregations, and do data enrichment. Because as much as we would like to have big freedom of data formats and whatever, if we want to get something reasonable from data, we need at the end data which are valid, cleaned, and structured in some way, and therefore discoverable. Only then we can actually use such data for analytic tools, machine learning, AI, whatever. So focus on these lower decks is to ingest data, no matter how chaotic, but at the end, have quality data, consistent data, and be able to trace data lineage. And what about upper decks? I talked about those rules which were missing usually in data lakes. So we need to have some order in this system. Therefore, data lakehouses have rich metadata, and they introduce catalog service for schema management. They implement robust data governance, quality checks, and that way they allow data to be consumed by different types of tools and departments in the company. Well, it was just a very quick overview. And this talk is focusing on data formats, but without saying a few more words about those data lakehouse upper decks, it would be difficult to understand all relationships. So let's quickly look at upper decks of data lakehouses. I talked about data governance, and people usually tend to see it as something very complicated, very boring, and very limiting. But on the other hand, we already learned our painful lessons about chaos in data stores without data governance. So if we want to have data which are meaningful and can be used for our business, we need to implement some rules of order. And there is a Data Management Association, which publishes this framework of data governance. Here is the title page of that book. It's a very big book and contains a lot of techniques and many use cases. And there are many articles which talk about data governance and emphasize how complicated it is, and that you shall better buy some products they offer to you. Yeah, well, if we are a big company, like thousands of people, dozens, hundreds of departments, then definitely yes, data governance is big task, and we need some tool and probably some some other company to implement it. But if we are a small startup, we can start with some basic rules, some understanding the data, our strategic asset that we need to implement, some basic data life cycles and data lineage. We need to ensure data quality. And the data must have some owners and someone who takes care about implementing all these things. Here we talk about data stewards. And we must understand that data governance is continuous process. It's not the place which we reach, it's journey, because our data application is evolving, and the same way we need to evolve also the data governance. In the past, there have been some really bad security breaches. So, in reaction on it, there are some rules, some law requirements like GDPR, Californian Act, and other norms which required implementation of data security and data privacy. So we need to be sure about who can access data. There is this principle of least privilege and only for limited time, which again, from the point of view of small startup, can look something very limiting and breaking like agile development, but losses from security or privacy breaches can be devastating for companies. So we must take it really seriously. And one of things which we need to ensure is anonymization of data or deletion or anonymization data at the end of their life cycle, because that was actually sometimes an issue in the past, storing data with sensitive information forever, because it might be useful in the future. We have now new player in this game, and this is artificial intelligence, which comes as new layer above all these things, and it promises a lot of magic. Fortunately, this AI hype is already fading. Users now recognize real-world limitations, and we now understand that effectiveness of AI tools in Data Lakehouse depends first of all on quality and amount of training data, and second, it depends also on use case which we have, because as we already all know, AI shines with topics which are nicely described on internet, and there are plenty of resources which can be aggregated into this large language model, but some niche topics are actually badly underrepresented. So if we have mainstream topics in our data lakehouse, well, there is a huge chance that AI will mostly be helpful for us. But if we develop something which is very rarely represented on internet, it's very niche domain, then here we will have a huge possibility for hallucinations, because AI will try to give you the best answer, and of course with not enough data, it will give us something constructed from testing data. Because we must understand that from the point of view of AI, there is no concept like true or untrue. AI gives us always the most probable answer based on training data. This is not an error. This is how AI works. So having some data, it constructs most probable answer from those resources. Imagine situation if we would have AI trained only on animation movies and fairy tales. We would ask something, then we will get the most probable answer from these fairy tales. It will be consistent in the world of fairy tales, but yeah, useless for our real life. And there are these well-known problems which come with these problems with training data, like overgeneralization, misinterpretation of data, overfitting, underfitting. I have several talks on YouTube. They were done during the time when we were part of NetApp, so they still have NetApp logos and NetApp style, but you can find all relevant information here in these talks if you would be interested. So, to summarize it very easily, if we want to use AI, we need to always validate those answers, especially if we work with topics which we know are wrongly or badly or very rarely described on internet. Okay, that was a summary of those upper decks, and now let's look at the data formats. So we all probably learned in hard way some lessons about storing data. So just to quickly sum up these learnings, we must collect the data with a clear purpose. Even those GDPR and other law rules that require that we collect data which are only data which are essential for our business operations. In the past, companies collected like hundreds of gigabytes, even petabytes of data because they could be useful in the future. They did not know exactly what to do with it, and that with those data sets at the moment when they collected them, so they store them for potential future use. Yeah, okay, this is nice. And what about return of investment from stored data? Because this is not the goal, not the main goal to have a huge amounts of data. Main goal is to make business out of them. So in the longer run, many companies they actually don't need to store raw data, huge amounts of raw data. They often are good with aggregated or summarized data, and definitely they must be cautious about those sensitive personal information if data or in data, which I already mentioned in data governance. We all lived through the era of race and slight downfall of relational databases. Some 15, 20 years ago, world of data was mainly relational, and there were all these limitations with storage coupled with computer resources. Those formats were mostly row-oriented, and that was sort of golden era of data warehouses. But scaling was very difficult. Then came the era of data lakes, and it was necessary because of new technologies which we started to use in new millennia, which required new storage formats and had different architecture. So, with these new technologies, the idea of decoupling computation and storage was born, and both of these areas could be scaled independently. And also, these new technologies brought a new concept of immutable and append-only data. Well, it was actually already true in the past. We just did not formulate it so clearly. And therefore, this era of new technologies and data lakehouse brought new formats. We all use JSON format. We all heard about Parquet format, and there are other like Auro ORC format. And out of these formats, Parquet format actually became the most popular one. And therefore, I will dive now deeper into it because those very specific, nice feature of Parquet data format are actually used in Apache Iceberg storage format, which is now a new uh, standard for data lakehouses. So let's look into Parquet data format. This format is now practically everywhere. It became de facto standard for data lakes and lakehouses, and it's columnar storage optimized for reading, and it is very efficient for numeric data types. Strings are less efficient. They are stored as a byte array. And this format supports different compression algorithms and is optimized for read-heavy workloads. It contains all metadata in that file. So if we have Parquet data format, we do not need any additional metadata outside that file to understand the content of the file. Here is a picture from Parquet format repository, which actually nicely illustrates this format. But to understand it, we need to talk first about how actually our data processed to be stored in a Parquet data format. So we, at the beginning, have normal data set as we know it. That data set is row-oriented, and it has some columns. And to be able to process it into Parquet data format, we need to do some magic with this. First of all, we need to divide that data set into row groups. And those row groups usually have like dozens of thousands or hundreds of thousands rows. And for our purposes, it is advantage if that data set is already ordered in some way, because it would help us to store data more efficiently. So here is some very simple example showing, of course, a very trivial structure. But here we can see that if we have that row group, we have these columns inside each row group. And since that row group contains only part of rows from that original data set, we talk about column chunks. It's not the whole content of the column, it's just what is in that row group. So here, this is clear. And now seeing this, we can actually turn this picture slightly, and we will see that we will have here row group 1, row group 2. Inside that row group, we will have a column chunk for column 1, same for column 2, column 3. And these column chunks will be divided into pages to have additional layer for organizing data, and inside those pages we will have those particular values from each row. And now, seeing this, we can understand that original picture, how that Parquet data format is actually organized. So here we have row group 1. Well, I should name it row group 0 because it's, of course, ordered from, it starts from 0, these numbers. So here we have this whole chunk for row group 0. Here is column 0. Or first column, they name it here A, and here is that whole chunk for column A, and that column is divided into pages, page 0, page 1, and inside is each page we have those rows which are actually stored differently based on data type, based on how many repeated values we have, and so on. So it's not like value by value, but it can be compressed in, it can use dictionary, whatever is necessary for storing it. So this way, you can see that we can very precisely read from that data file only those columns which we want. And to be able to focus reading operation even better, there are rich metadata in Parquet data file. And metadata are stored in each page, but the main part of metadata is at the end of that Parquet file. And here we have all sorts of information which we need to optimize reads from Parquet data file. There is, of course, schema, because that file is self-describing. Here we can have some additional key value pairs for whatever reason we would need for understanding the content. We have separate metadata for each row group and each column, and one values which are in these metadata are also minimum, maximum for particular column, how many distinct values we have, how many nulls we have, and all this stuff. These column statistics allow us to skip irrelevant row groups or pages. So if we dive deeper into these metadata, we can optimize our query very nicely. And here is some idealistic picture showing how we can actually prune data for query processing. So if we have query, first level of pruning is partition pruning. Partitions in the scope of storing data in data lakehouses, partitions are groups of those Parquet data files, which are grouped together based on something, dates, places, countries, whatever. Typical. This is the same as partitioning in relational databases. It's just organized on the disk, and we have files, not directly tables. So if we have query, we can do first pruning on the level of partitions. Say for our query, we will need only this and this partition. limiting amount of data files for processing. This way, we can go further because now we read metadata from those Parquet data files, and we now see minimum, maximum for those columns which we want to read. So we can now say, okay, I need only this and this data file. And with even deeper dive, we can now say, okay, I will read only this column and this column. And from these columns, I will read only page 0, page 1, page whatever. And this way, we limit original huge amount of data, which like data files which are stored in many partitions. We limit these data reads maybe even to few data pages, which actually contain data which we need. And that way, we can optimize our query very nicely and get data output very efficiently. Okay, it was a deep dive into Parquet data format, but it was necessary because for understanding of Apache Iceberg, we need to know about this magic in Parquet data format because Apache Iceberg actually uses all this Parquet magic. So, what is Apache Iceberg table format? It was originally created by Netflix and outsourced, and Apache Iceberg is a table format for large analytic data sets. It supports versioning, including version rollbacks. It allows ACID transactions and schema evolution, implements hidden partitioning, and also partition evolution if we define on the top of it partitions on our own. It also allows time travels to query historical data using snapshots, but it is, of course, intended mostly for immutable data, append-only data with very minimal updates and deletes. So let's look at the architecture of this table format. And this is first thing which we must understand. Iceberg is a rich table format. It's not a database engine. We can't run Apache Iceberg as application. Apache Iceberg support must be implemented into some engine. Core libraries for this format are in Java, and there are separate projects for Python and other languages. And this table format is already supported by multiple engines, mostly those engines which are Java-based. But it's already being added into also other software and also into relational databases. This table format aims to allow multiple applications to work on the same data and to ensure all these things about ACID transactions and consistent snapshots and whatever. There are three layers of this format, which we will now dive into. So first of them is catalog layer, the very top layer, which stores schema definitions and information about where data are located. Middle part is metadata layer, which actually contains all these snapshots and information about partitions, state of tables, and so on. And on the very bottom, we have data layers, which are mostly Parquet data files. Could be different format, but Parquet is most optimal, at least in these days. So what about that top catalog layer? This is like entry point into any Apache Iceberg dataset. It is source of truth for latest snapshot and schema, and those catalogs can be either active, like implemented in Hive or Amazon Glue, or could be simple JSON files which we need to process, and their reference to metadata layer. That Hive meta store is most common catalog if we have on-premise implementation. And there is also a very interesting implementation in streaming database called Rising Wave, which hosts catalog and metadata in Postgres. I will show it on future slides. So this is catalog, and if we read data from catalog, it points us to metadata layer. And that metadata layer contains several objects, metadata files, manifest lists, and manifest files. Metadata files are immutable JSON files. Those other manifest lists and manifest files are usually Avro data format. And all these files are immutable, and they build hierarchies. Each level of hierarchy consists from these three same types of objects. Every change in underlying data layer creates new layer of metadata. And these metadata files, each metadata file defines consistent snapshot. And these snapshots are used for time travels and rollbacks and all these schema evolutions, partitions evolutions, and so on. So from catalog, we get information about the latest metadata file, which contains the last consistent snapshot. From metadata file, we find a manifest list pointing us to manifest files, and manifest files either point us to the lower level of metadata or directly to data layer. Depends on how many hierarchies we have. When we read all this metadata, we actually find all information here for proper data pruning. So now with metadata read from that middle part, we can go into data layer, and here we read precisely those Parquet files and those specific parts of these files which we need for getting results of our query. Those data files are, as I mentioned, immutable and append only. Therefore, if there are some deletions or updates, all these changes are actually stored in that metadata layer. So if we find out that there have been some changes in data, we must now actually once we prune data for query, we must apply all these changes to get proper content of data. And you can imagine if there would be several layers of these changes, processing of all these changes could be quite slow. This is why strong recommendation is to really avoid updates and deletes in data as much as possible. Of course, not always possible, but now you see on this structure that if we would try to deduce changes too often, it will slow down the whole processing. Well, there is some mechanism for actually merging these changes, but it requires also some regeneration of those data layers. So we should be careful about these operations. But this is beyond scope of this talk. So let's now look into last part, and this is how Postgres is sailing with icebergs. If we look at Postgres and Data Lakehouse solutions, we can see two main solutions. First of them is Postgres in Lakehouse solution, meaning Postgres is integrated into a larger platform, and that primary platform is mainly open storage layer, and on the top of it there are some primary processing engines like Spark, Flink, whatever. And Postgres is used in very specific parts, like can be used at the beginning for collecting of some types of data, can serve as a gold layer data store and meta store. We can use that rich foreign data wrapper support to make it a federated query engine. That way we can use the best of all those worlds, but of course we must understand that such a system becomes very complex, and over time when the system evolves there could be some performance bottlenecks in different parts. Yeah, this is how our lives go on in these data processing applications. Another solution is Lakehouse in Postgres, meaning Postgres functions in this solution as a single-site lakehouse. This is ideal solution if we implement a lakehouse on premises, or if we have a relatively simple implementation. It's easier to manage. We have lower total costs on ownership. And basic structure of this solution is Postgres with Iceberg. Big advantage is that we can reuse all knowledge which we have about Postgres ecosystem. It is also attractive for all-in-one transactional and analytical solutions. Here we talk about hybrid transactional analytical processing. And of course, pros is that it's simple, we have lower costs, and we use familiar tools. But disadvantages also well-known: scalability bottlenecks and performance bottlenecks. Well, it can be improved using some tools. We will look at it. But before I will dive into these extensions and tools, I need to talk at least partially about DuckDB database. This is very interesting new analytical database which was created by Institute of Mathematics and Computer Science in Amsterdam. This is the same institute which is credited for Python and MonadDB. And this is single node database intended for embedding in other applications, and it's actually analytical replacement of SQLite. It's open source, column-oriented, it has in-memory processing engine, it's designed for heavy parallel analytical workloads, and if you use it, it feels like Postgres because it uses Postgres SQL parser and SQL dialects with some interesting improvements. I actually have a talk about Postgres and DuckDB. Here is a link to that recorded talk on YouTube. I presented that talk in Postgres Meetup for All. And here you can find many interesting use cases how to combine power of Postgres and DuckDB together. And this DuckDB is reused, embedded into some solutions, which I will talk about on this next slide. So, which solutions for Postgres and Data Lakehouse we already have? Actually, we have very nice solutions. And I mentioned those, I would say, mostly discussed ones. First of all, this is Cybertech Lakehouse, which integrates transactional and analytical workloads also with AI. Second is Crunchy Data Warehouse, which extends Postgres with DuckDB, and users can create and query Iceberg tables directly from Postgres. Third is Databricks Lakebase, which uses special Lakehouse IQ engine. They emphasize that this is Postgres compatible transactional database which supports Iceberg tables. And fourth solution is a Google Alloy DB, which they describe as Postgres clone with columnar vectorized engines, and they claim how much faster it is for transactional or analytical workloads than Postgres. By the way, in these days, many databases now claim to be Postgres compatible, whatever it means. It is for another discussion what actually it means, Postgres compatible. But I pointed out, because this is also one thing, Simon Riggs talked about in that talk in December 2023, that we will see more and more databases getting closer and closer to Postgres. Very quickly, because time is almost up. Here is that rising wave distributed SQL engine, which I talked about. It's streaming database. It processes real-time data streams and stores only those aggregated values. And it is a very efficient solution for applications which require high-speed processing, and it is used for critical applications like fraud detection, stock market analysis, some very critical types of monitoring. It has built-in support for Apache Iceberg tables, and they claim that Rising Wave is fully compatible with Postgres, and it uses Postgres internally for storing that Apache Iceberg catalog and metadata storage. Very interesting. Definitely want to look at it deeper. We have also some other solutions for integrating Postgres and data lakehouses, and here we have some extensions which we can use in Postgres. First of them is ParadeDB. This is Postgres integration with Iceberg, and it is a very promising solution, and I highly recommend to look at it deeper. Second is extension PGDay, which integrates Postgres with DuckDB, and it's developed by team which actually created DuckDB database, so integration is done very nicely. We have also this Citus distributed columnar storage for Postgres, which we can use for horizontal scaling. And we can mirror Postgres tables into Iceberg tables using PG Mooncake extension. And for using directly Parquet data files, we have several extensions which allow us to read, write Parquet files. Some of them also on Amazon 3D storage and so on. And last but not least, we have Postgres foreign data wrapper for federated queries between Postgres servers. It's quite obvious, but I think it's necessary to mention it in this scope because this creates a richer environment. And as Simon Riggs said on that talk, in 20 years, maybe everything will be done in Postgres. And in that scope, I really like this picture showing how many extensions we already have for Postgres to integrate Postgres with other tools And that way, we are able really practically process everything in Postgres. Here are some additional resources. I already linked resources in previous slides. Here are some additional ones which you can use for getting more information. And this is all. I thank you very much for your attention. If you want to find my slides, here is QR code. Here you can find my other recorded talks. And I will now stop recording and we can dive into questions.